Good morning, everyone. So got a ton of people coming in. Now's a good time for you to ask me questions you might have. Anyone? Anyone? Maybe it's my morning. Maybe it's my evening class. I had a lot more students, but I thought it was you guys. You can tell I've been paying attention to the roll a lot. Otherwise, I'd know that off the top of my head. All right. Well, I guess I'll go ahead and just start talking about the topics. Doesn't seem anybody has any pressing questions right now. Today, we're actually going to start into quantum mechanics, and that's part of modern physics. So in the late 1800s, early 1900s, everybody thought physics was pretty much done. It was like the vast majority of scientists, if you would have asked them, they would have said, "Oh yeah, we've sort of figured everything out. It's just a matter of making sure Newton and Maxwell are right to 8 decimal places instead of 3 decimal places." And that's maybe there's a few things, little details we got to figure out, but we pretty much figured everything out. There's nothing going to be any shocking or anything. Then, like I said, there was a couple experiments outstanding that people were having a hard time understanding, and I'll be talking about those today. And then, of course, once you start doing that, figuring that out, that begets new discovery. And in fact, we had two major revolutions in the early 1900s, and that's called modern physics. And the first of which was or the first complete one was Einstein's theory of relativity, and then Einstein's general theory of relativity, which he did more or less on his own, which is really super impressive. And it's also super impressive that people just ran with it. They're like, "Oh yeah, this is completely obvious now," even though it's completely weird. It's somewhat obvious. He's got the proof that he showed. He's managed to prove some things we already didn't know. He's managed to explain, predict some things that we hadn't seen yet. And then when, for instance, starlight was shown to bend, that was his proof of general relativity. Special relativity could explain a lot of different things as well. So that was a really big deal, but it was done basically in one fell swoop. At least the special relativity was, and then the general theory was sort of helped a little bit more along by other people, but generally the special theory was done just by Einstein and completely out of his head. So it was really an impressive thing. Unlike that, quantum mechanics, which was the other major revolution of the early 1900s, started really in 1900 and continued developing. Honestly, it's maybe not still developing now necessarily. There's still some things we're trying to figure out about it, but it's pretty it's pretty much a done deal, and it was definitely a majorly done deal by the 1950s, 1960s. But through 1900 through 1923, that was when we were hashing everything out. Uh, and that's when we start coming up with Schrodinger's equation and Heisenberg's equation. And once you have that and then the Dirac equation, you basically have a complete quantum mechanics. It's more or less a matter of trying to interpret what it means. So that's what we talk about when we're talking about modern physics is quantum mechanics and special relativity mainly, but also general relativity. So that's what we're going to talk about today. But also, I want to close the loop on chapter 20, which was the second law of thermodynamics. And I introduced entropy. I even gave you an idea of what it was. I told you it's dq or ds, which is actually a state variable, which I'm going to talk a little bit more about that, is equal to dq, which is not a state variable, over t. And remember what I mean by not a state variable. That means when I put a differential like a d in front of it, it's not really a true differential. It's not what we call an exact differential. And so I have to write a d with a bar through it and call it d bar q. I don't have to, but it's better to do so, at least from a mathematical and physical standpoint, because to have a regular d suggests something that can't be done. So in terms of that d bar exact differential and all that stuff that I was talking about, this goes back to what we learned in electricity and magnetism when I told you that if you found a curlless field, so for instance, the electric field E, del cross E is equal to 0, period. No ifs, ands, or buts about it, right? Well, sort of. So anyways, del cross E is equal to 0. That means a bunch of things come out. Because that's 0, we know that a potential can be created. In fact, it's a potential such that the negative gradient of the potential is equal to the electric field. It also means that the integral of that potential from A to B is independent of the path that you take from A to B. And it also means that the integral of that potential over any closed loop is always going to be 0. And remember, it was all those things that I listed, and it said if one of these are true, then all are true. Well, notice that's true about V. V has this integral thing. That's, in this sense, V is a state variable. V, or U is what we use. U, the electric potential, or V, or potential energy in the case of gravity, or V, the electric potential, which we use in electricity and magnetism. That is a state variable. That's something you can write dV on. It also happens to be related to an exact differential, which you'll learn in differential equations, where if f is a function of, say, x and y, then df is the partial of f with respect to x times dx plus the partial of f with respect to y times dy. And if you find a differential equation like that, you can solve it by realizing that the second derivative with the opposite variable will always be equal for each of the terms. So if you got df dx in the first term and you got df dy in the second term, but you don't know they're that, you're just trying to test it, then you can take the derivative of the one in front of the dx with respect to y, and you can take the derivative of the one in front of the dy with respect to x. And if those two things are equal, then you know that that's an exact differential equation. You can solve it with a very simple method. And those are things that beget exact differentials. So in some sense, they're like functions. But all those things that we talk about that we can put a d in front of without the bar on, those are all exact differentials, and therefore those are all state variables, or state equations, if you will, equations of states, another way of saying it. So that's what entropy is. That's what that's what internal energy is. That's what electric potential is. There's actually a magnetic potential, but it's only exists in certain really rare scenarios. So you can't really apply that one very well because it's basically made up, and it's not even that. It's not a scalar potential. It's a vector potential, and only in certain cases can you make it that a scalar potential. So that's just something bigger to understand about science, is that we look for variables that have that exact differential nature because those turn out to be important. Not because we necessarily assume they were up front. We just over time learned that they were. So this new one that we introduced in chapter 20 was entropy, which I did it actually in chapter 19, but in chapter 20 it's called entropy, and it's a measure of the disorder of a system. And basically a version of the second law of thermodynamics says that the entropy of the universe will always increase, or the entropy of any closed system will increase or at best stay the same, and it only stays the same during what we call reversible processes. And reversible processes are ones that are like quasi-static. They stay perfectly still. They're just an infinitesimal move from a equilibrium state to another equilibrium state, and it can happen somewhere between there. So they're really things that don't happen. We can approximate them in some ways, but other ways that same approximation fails. So you got to be careful with that sort of stuff. So in general, there's no reversible processes, but if you found one, I don't want to say there's no reversible process. There's no real useful physical processes that are reversible. But if you found one, for instance, then the entropy of the system would stay the same. So generally speaking, entropy increases. That means disorder increases. People have used it to explain things, and I like these analogies, even though they're really hard to nail down exactly what they mean by it. But for instance, it's really easy to pull out of a parking space, but it's hard to park. Relatively speaking, it's harder to park. And you can imagine it this way. If this is a parking space, let's say this is a parking space. Okay. And let's say this is a three-wheeler you're trying to park. Now, a three-wheeler is going to be a lot easier to park in a tricycle, motorcycle, tricycle things. It's a lot easier to park than a car is, but it's still the same laws that apply. when you're pulling into a parking space, you're going from all these different states. Okay, there's billions and billions of them, to just a rare few that if you play by the rules, and not everybody does, you have to stay in between the lines. So you can go over here, you can go over here, you can go over here. All these are different states. Notice those number of states that you can be in that's technically in the parking space is very few compared to all the ones you can be in out here. So having a bunch of micro states is what we call them, is a relative measure of disorder. So if you have a bunch of equivalent microstates, then you're in a state of disorder. But if you have a very small number, then you're in a state of high order. So yeah, there is like an infinity of ways to park, but that infinity is way smaller than the infinity of the ways not to be parked, right? All these things are all true, right? So that's one explanation of it. And it turns out that's actually a fairly good one, because it leads you into the idea of number of states being the measure of entropy. And if you look, your book in chapter 20 near the end says that S equals K times the ln of W. Sometimes they'll use capital omega, where omega or W is the number of states that are available. And that was a really big deal, and that's something that helped us out through quantum mechanics as well. So that's really the ultimate version, if you will, and that's something you'll learn a lot more about in your engineering thermo stuff like that. Even though they're much more application oriented in engineering thermo than they are in a thermodynamics in the physics class. I would highly recommend you taking a thermodynamics class under a physics department as opposed to engineering department, but do that in addition to your engineering one, because you'd be surprised how many little details you don't get from the big theory one that we do in physics versus the one that you do in engineering. And then there's even a lower level, quote unquote lower level, or more applied level of engineering called steam table thermodynamics. And that one's actually very useful as well. But if you're going into something like mechanical engineering or aerospace engineering, maybe even not necessarily civil, but chemical engineering, nuclear engineering, I'd say all of those engineering fields you would greatly benefit from having both versions of thermodynamics that you get from a physics department, as well as thermodynamics you get from an engineering department. So keep that in mind. I'm sure they'll allow you to take it as an elective. It is going to be a lot more mathematical. The good news is it's almost all derivatives. There's integrals too, of course, but the vast majority of physics in thermodynamics is about taking derivatives to find new laws, Maxwell's equations and stuff like that. And then, there's Laplace transforms and Fourier transform, well, not Fourier in thermo, but so there's all these neat little transforms that can change enthalpy to entropy to Gibbs free energy, all that cool stuff. So the other versions of the second law of thermodynamics is the one I told you. It's sort of the most simple to understand. Is heat's not going to flow from a cold object to a hot object on its own. You have to force that to happen, and you're going to pay some loss in energy for that. But on its own, and they use the word spontaneously here, heat will flow from a hot object to a cold object. So that's why if you just sit outside, you could have a heat shirt. Just sitting outside, you don't have to do anything else, just sit there, because the temperature is higher than 98.6, and overall, eventually, that could bring your 98.6, which is average body temperature, that could bring it up to higher than that, and it doesn't take much of an increase in the body temperature before it's a dangerous situation. So that's just heat from the environment flowing from the hot air environment into you, which is also hot, but not as hot as the other thing. So it's heat flowing from the hot object to a cold object. That's also why you can get hypothermia even in the Caribbean. So you can, fall overboard from a cruise ship in the Caribbean, which, the water temperature is sometimes 82 degrees. And that feels so nice and warm. And in fact, like my pool is 97 degrees. That feels warm or nice and warm. That's why I should put quotation marks around the nice part, not the warm. I don't like it. It's not that comfortable for me, right? But if you even fell in that at 96 degrees or 97 degrees, that's still a lower temperature than your body temperature. So heat is spontaneously going to leave your body and go into the water to heat it up. Now, those bodies of water are not big enough to heat up a significant amount by your body heat. So it's going to keep draining energy from you, and therefore you will get hypothermia even in 84 or 96 degree water. Okay, so that's another version of the second law of thermodynamics. And what I'd really like you to do to focus on chapter 20 is think about that problem that I worked for you yesterday or last time, where I showed you, you know, putting a piece of metal in water and the water heated up and the metal cooled down, right? And then I calculated that conservation of energy says if the exact opposite happened, meaning you took metal and water in an aluminum cup and stuck them all together at all at the same temperature of 20.26 degrees Celsius, that spontaneously heat could flow from the water, making it colder. Instead of 20.267, it's going to now be 20 flat. And now the gold that I threw in there is going to be a temperature of 100 degrees Celsius. That can't happen by the first law of thermodynamics. It doesn't violate conservation of energy. So I would like you to be able to do that problem and then say, okay, let's calculate the entropy change. Now the temperature change is very small, at least for the water. So you can use approximation that the change in entropy is the heat loss divided by T, the temperature. So if you calculate the entropy change on that, you'll see the entropy actually increased on the way that it happens, whereas it decreased on the way that it doesn't happen. So if you can do that calculation and you can take the time to write down all the versions of the second law of thermodynamics, and you have more than enough information to pass chapter 20 stuff on the final exam, okay, and on the test for that chapter, depending if we have it, which I think we will. So that's really all you need. If you do the homework, you're obviously you're getting that learning, and that's why the homework's there, even though it's a lot bigger than what I covered. So that's it for chapter 20. That's all I wanted you to do, is do the homework, so you'll have done them. So you'll have done things like, you know, use the ideal gas law and use the adiabatic expression, P times V to the gamma power is equal to P to V2 to the gamma power, where gamma is Cp over Cv. Using the ideal gas law, vapor pressures, all that kind of stuff. So just doing those types of homework is more than enough to make you better understand the concepts behind it. And then all I'm asking for you to be able to pull off is that one calculation. Everybody, do I need to repeat that for anyone? Okay, be able to do that one calculation showing me how the entropy changes in the case of water, aluminum cup, and gold all being at the same temperature, and then spontaneously the water and the aluminum cup cooling off and the gold sample turning up to a heat of 100 degrees Celsius. You know, you should be able to show me how that change in entropy is actually negative. Okay. All right, so that's it. That's all you need to do is know that, and all those versions of the second law of thermodynamics. Be able to at least memorize them and recognize them verbatim. Okay, I would ideally like you to understand them, but that's not a trivial task. But I'm certain that several of the versions, like the spontaneous heat flow, are easy. You can understand that perfectly well.
So, there was another way actually I learned about how to show entropy that I had done before, but it was taking each one of those systems and just like putting, like, for example, the gain of energy between the freezing point and the boiling point, and then when you're doing, like, for example, the phase change, you have that separate too, and then you have, you know, a phase change again separate too, and you just stack them and you add them together, but you're keeping track of which direction that they're going, and so you can make it negative or positive that way.
Oh, gotcha.
That makes sense. So if you're going up, you're making them positives. If you're going down, you're making it negatives.
Yeah, right.
And when you add it up, it will show if it's negative or positive.
Yeah, that would make sense. And that also allows you to figure out the signs with the heat of vaporization and heat of fusion stuff that I told you is such a pain in the butt to figure out. I mean, it's not that much of a pain, but it's something you got to stop and think about to keep from making a careless sign error if you use delta Q equals 0. But yeah, doing that will actually help you discern that sign as well, even though you're talking about entropy. But yeah, absolutely. If you're talking about something in a solid state, that's a very ordered state where you have atoms or molecules in a regular array or matrix, if you will, and that matrix is a highly ordered state. There's still some vibration in it, but it's a few number of states that you can put that in, such as in a solid state. Then when you go into a liquid, it's sort of a hodgepodge of balls rolling all over each other. And then when you go into gas, they're not even rolling over each other. They're, tens of diameters apart. So yeah, that's good. So yeah, there's a lot of cool ways to think about it. There's a lot of nice things, and they can keep you from wasting a lot of money. I mean, suckers are born every day, and people are willing to take advantage of them with all sorts of phony machines and generators and stuff like that. And if you just think about the second law of thermodynamics, you can, if you really think about it deeply and look at all the energy sources, you'll see something that seems too good to be true almost always is. Okay. All right, so let's jump into the section on quantum mechanics, which is chapter 37. So I'm going over basically the historical development of quantum mechanics, because it turns out that story is really an intriguing one, and it gives you a nice little set of parallels of how we figured out what was what and where these equations came from. And I think when you have that story in your head, it's much easier to understand it and then know the relevance of the equation. So let's try that. Sorry, I haven't had breakfast. So what I do is, and I never eat breakfast, I just drink coffee and then I go to lunch. But when I don't eat for this long period of time, I literally start sick on the stomach. So I got to keep drinking my coffee. The chapter 37 is called Early Quantum Theory and Models of the Atom. So as I said, in the late 1800s, early 1900s, people thought science was done and blah, blah, blah. Well, there was these outstanding experiments that were kind of weird. And one of them was the intensity of radiation put off by an object. So when you heat something up, and it's actually true, period, as long as the temperature of something is greater than 0 Kelvin, then that's going to put out radiation. Now, we normally can't feel that radiation. In fact, we don't feel it until it gets around, 1,000, 2,000 Kelvin. Then we can feel the radiation coming from it. But generally speaking, we don't feel radiation coming from things. So we don't really think that much about it, but the scientists do, and they knew what was going on. And they knew that there was a very distinct relationship between the intensity of radiation on the vertical axis versus temperature on the horizontal axis, or versus wavelength on the horizontal axis, or in 3 dimensions, you could say temperature versus wavelength and intensity versus wavelength and temperature. That's the holy grail of it all. There were equations that were arrived at. So for instance, Lord Rayleigh, who, if I remember correctly, was an American who happened to spend the end of his life, most of it being somewhat of a Ben Franklin type in the most negative way. So, Ben Franklin was all about women and loves living in France because they treated him like a rock star there. So he spent the end of his life basically in France. And that's sort of what Rayleigh did, is he became Lord Rayleigh and spent a good deal of his time chasing women and trying to become rich. But nowhere near the statesman or the awesomeness of Benjamin Franklin, by the way. But Lord Rayleigh was there at the time of Michael Faraday, and Lord Kelvin was a little bit older than him. But he had come up with a nice equation, and then Jeans added to it. So there was this equation called the Rayleigh-Jeans equation, and that gave the intensity really versus the frequency or wavelength, whichever one you want to call it. And you can see that on page 988. That was a frequency versus, intensity versus frequency graph. And that's the Rayleigh-Jeans one. And basically it just went up like this and went up straight up. So it was sort of almost like a parabola initially, and then it just went almost linear from there on out. When they started studying these objects, an object that you could study is literally like a horseshoe stake. You pull a horseshoe stake out of the ground, you throw it in the fire, and then it slowly changes its temperature. When it changes that temperature, you start recording the intensity for all the different wavelengths of radiation coming from it, and you would get a graph. And the graph actually looks like this. It's really, really gradual on the low frequency side, and then it drops off rather rapidly on the high frequency side. That's what the experimental results are. Now, Wien, who we'll learn about Wien's law as well, Wien had actually come up with another equation that fit the shape a lot better, but it still was not right. It just didn't work very well, and everybody knew it. And it was called the ultraviolet catastrophe because basically it failed in the ultraviolet portion of the spectrum to accurately predict. And really, that's more talking about Rayleigh genes, more so than Dean's law. And Dean is spelled W-E-I-N, by the way. So let me, well, actually, let me go ahead and finish doing the discussion. So we've got that issue, this black body radiation, and black body just means the ideal scenario. It's the perfect emitter and the perfect absorber. So if you look at it, it's going to look perfectly black, like you can't see any depth in it or anything like that. A good example of a black body, or at least an apparent black body, is if you see a stack of pipes all stacked on top of each other like this. You look at the ends are just pitch black circles, because there's almost no probability of any light that could bounce around there and then come right back out at your eyeball, because it's just going to go all the way down the other end of the tube. Now, if you get lined up just perfectly, you can see down one of them, but all the other ones are still going to be black bodies. So that's an example of a black body, and it's sort of an idealization that we can use to allow us to get a physical grip on the situation, and then do the calculations theoretically and try to predict how atoms are behaving and stuff like that. So that was one of the problems that existed, is when we made that intensity versus frequency, or intensity versus wavelength graph, it just didn't work, right? And we didn't understand why. Another problem that existed was we didn't really know. One, we didn't even know that atoms were 100% there. There was not 100% consensus that atoms existed. In 1905, Einstein wrote the Brownian motion paper, which could have won the Nobel Prize, and that proved definitively the existence of atoms. But even that little aspect was controversial until then. I mean, literally, Einstein put the final nail in the coffin of the idea of atoms not existing with that paper. But what we did have was this idea that if they exist, we want to know how the matter is distributed throughout. So there was this ongoing problem of how is matter distributed throughout if these atoms exist or if they don't exist. So there's that problem going on. And then there's another problem going on where basically chemists see some hope in being able to identify elements, compounds, and stuff like this from a certain experiment. So if you take a test tube like thing and you suck all the air out of it and you seal it off on both ends, and then you melt just the end just a little bit and let some element in there, let's say helium or hydrogen or mercury vapor or any kind of gas that you want to in there. And it could be a mixture. It doesn't have to be an element or a compound. It could literally be a mixture. But if you do that, and then of course put a little electrode in each end of that sealed up test tube that only has that gas in it mostly. I mean, obviously you're going to have some air that leaks in, because we're human, we can't make it perfect. But still, the vast majority of it's going to be argon or helium or whatever. And then it's got little electrodes on the side. And now you take that tube, that glass test tube that's sealed on both ends that only has a gas in it, and you apply a buttload of voltage across it. I'm talking 500, 1,000 volts. Okay, stuff like that. This you might recognize as basically like a fluorescent light that you'd see in a store or maybe in your kitchen. Okay, it's got basically a high voltage end and a low voltage end, and you're putting so much voltage on there that it's exciting something inside and light comes out, right? They knew this. They could do this, and not only that, they could see that, oh wow, when I do this with hydrogen gas, I get these very distinct lines. They call them the Balmer series. And when they do it with helium, they get an entirely different set of lines. And they do it with water, they get a different set of lines. When they do it with mercury, they get a different set of lines. Neon, and I say neon because they are neon lights, in fact. All of those things give different ones. So chemists are like, well, if we can understand how this is working, we can see definitively whether this is like fingerprints for compounds. So it's something very super valuable. And in fact, we use it all the time now in astronomy and NASA and stuff like that. When recently, when we had a chance to see a craft run into the moon, that was our chance to see something get so hot that it's going to display that effect. So we looked at it with the right devices to spread the radiation out in different frequencies. And from that, we were able to detect that there was actually water below the surface of the moon. That's the kind of stuff you can do with it. So that was a big problem going on as well. People didn't understand it. And it was so big and famous that, literally like a high school or middle school math teacher had derived an equation for it that was exactly right. I mean, it could predict exactly the lines that you saw for hydrogen, and but it was purely purely empirical. It had no understanding of why. It was just, hey, curve fitting, right? Hey, I can make this curve, but it gave a structure to the mathematics that should be responsible for it, and that gave people a target to try to hit. So it was really valuable to have that. So those are three of the really big problems going around. A fourth one is called the photoelectric effect. And the photoelectric effect is basically that when you shine light on anything, really, but metals do it most easily, light can actually create a current. So you imagine light shining on a piece of metal. That light, which we now know as electric fields oscillating up and down, remember from Maxwell's equation. So it's electric field oscillating up and down, magnetic field, which is way smaller than the electric field, oscillating sideways, right? And then going a third mutually perpendicular direction. So you can imagine those waves doing that to atoms in a metal are going to take the electrons and cause them to wiggle back and forth really quickly. And in fact, if they're energetic enough, they should break loose. And then that could actually cause a current, meaning if somewhere away from that atom, there is a positive voltage, then that electron is going to fly to that positive voltage and be read as a current. That's called the photoelectric effect. And you could predict that was going to happen by the wave nature of light, only the results didn't really match reality. So the results from the wave nature of light is that the higher intensity of the light, the bigger the current. And the frequency should have no effect on it. Both of those are not true, though. In fact, the intensity didn't matter at all. In fact, what you can do is you set up the actual metal, and then you put a voltage across, basically where there's a plate behind the metal and a plate in front of the metal, and you can adjust the voltage so that you try to stop that current, and then you'll only get the most fast of electrons that have escaped. And when you do that, you find out that it's an entirely different relationship, but you can adjust it that way. And that's the experiment that we're going to do in my lab today. It's called the Photoelectric Effect Lab, but we're going to do it with a simulation software. So this was a problem, and the wave nature of light predicted results that were not seen. So one of them, for instance, was if you use low intensity light, it's going to take some period of time for the actual electrons to get resonant energy enough to be slung out and then create a current, where it turns out that if you have the right frequency, a single, what we later determined was a photon of light, a single photon of light will knock out the electron and actually give you a current. So that was inconsistent with experimental results as well. So those are the four big problems going on. What is the nature of matter? How is matter distributed within a solid object? Is it in atoms? And if it is in atoms, how is it distributed within the atom? What is the way to properly describe that intensity versus wavelength, or intensity versus frequency? What is the real root of the photoelectric effect? And then where the crap are those spectral lines coming from? Okay. And in fact, they even had different sets. They had the Balmer series, the Lyman series, and the Paschkin series. And I think Balmer, if I remember correctly, was the mathematician teacher. And actually, he was a very, he turned out to be a pretty brilliant guy. He was sort of not being able to get a position in the university anywhere. So he was teaching in an all-girls school. So he was really treated like a third-class scientist. But he turned out to be really, really good. And I think his name was Balmer, if I remember correctly. But that was the guy that came up with the equation. So those are the big problems we're facing. And now we're going to talk about the solutions to them. So first off, I want to start with that one about the intensity of light coming off a heated object. Okay. And that was the one that was coined the term ultraviolet catastrophe, because again, the Rayleigh Jeans equation failed miserably in the ultraviolet portion of the spectrum. So what we knew was that the intensity of radiation, and remember intensity, we learned last time, that was the watts per square meter that we identified with the Stefan Boltzmann law, sigma t to the fourth and all that good stuff. That intensity of radiation as a function of, let's say, wavelength, and you could do frequency, either one, because we know radiation is at least in the waveform is V equals F times lambda. So the V is the same for both cases. So they're really just a multiple of each other, the frequency and wavelength. And what we had was a Rayleigh-Jeans equation, and the Rayleigh-Jeans equation looked like this, and basically just went linear. And what we also had was a Wien's equation that went like this. And this is Rayleigh-Jeans. Okay. And the actual data, on the other hand, look more like this. Actually, it's really steep on this side, and then it was sort of gradual on this side. Okay. So there was some correspondence, of course. You can see how Wien's law sort of obeys it, but it doesn't mathematically work as well as it needs to. Okay. But this is the actual experimental results. So a guy by the name of Max Planck, Planck, where we now have a constant named after him called Planck's constant. He tried to work this problem over and over and over, and he was really a powerful theoretical physicist. He was really brute force, the guy that could calculate anything no matter what and would always get an answer, right? And he was one of Einstein's idols. And his idea was, like everybody else's, was to imagine the black body, the object that's emitting the radiation, was made up of little atoms separated by springs. And then there'd be another row down here, of course. And then there'd be another layer back behind that, of course. And you just treat them as springs again. And I've told you why that's useful. Remember when we talked about, or probably whoever you had, when you talked about wave motion and simple harmonic motion, the case was made that, we don't study springs because they're super interesting. We study springs because in some way at near equilibrium, everything behaves like a spring. So that was the idea. You're going to do this. And what he was doing was trying to say, okay, well, these are springs and they're going to resonate when a wave hits it and blah, blah, blah. That's going to make it give off certain amounts of energy. And that energy is what we're seeing here. And the energy that's being given off is specifically a result of Maxwell's equation, because remember, Maxwell's equation says that basically whenever you have a accelerating charge, the accelerating charge is going to put out electromagnetic radiation. So that was his plan, was using the electromagnetic radiation from that to do it. And he kept failing and failing and failing and failing. He couldn't get the equation to behave the way it was. So he used the trick that most physicists have long forgotten. But it's basically an idea where you pretend like a particular variable is, instead of being a continuous variable, like let's say in this case, it actually was the frequency. So you can imagine frequency being any number between 0 and 1, and you actually have an infinity of frequencies that would be allowed. You could also imagine frequencies being any number from 0 to infinity. And in fact, in between the 0 and 1, there'd be an infinite number, as well as there'd be an infinite number between the infinity and 0. Those are continuous variables. There's no holes in the number line that aren't represented by a number. There's, irrational numbers like pi, like e, and stuff like that, but they exist. There's no holes in there. You're not going to skip any digits. Okay, that's a continuous variable. His idea was, and again, like I said, this is a fairly common mathematical technique, was to pretend for an instant that a variable, in this case frequency or energy, was a discrete variable. And you could say the difference between two adjacent discrete numbers. So for instance, if you said things were whole numbers as opposed to discrete numbers, then it'd be like 0, 1, 2, 3, 4. And you could say the difference between 1 and 2 is 2 minus 1 equals 1. But you'd call that, say, n. And as you let n go to 0, then that discrete set of numbers would actually become a continuous variable. So that was the plan, is you treat it like it's discrete. You work out as much of the math as you can get through, because that frees you up from having to do calculus on things that you can't do necessarily. And then in the end, you take the limit as n approaches 0, and you get back to the discrete variable. Well, it kept working and looking really promising until he went back to making the variable discrete. So he finally just said, well, here's the result. I don't know what the crap it says, but this is the result. And basically his result said that the intensity of the radiation, I, as a function of wavelength and temperature, is equal to 2 pi h c squared times lambda to the negative 5th power. That doesn't look very much like that experimental graph, does it? But look at this part in the bottom. This is where it really gets hairy. E to the, and I really need my glasses, good Lord. Whew. Yeah, I thought I was seeing a negative there, but I wasn't. So HC over KT. And that K is the Boltzmann constant that we talked about before. So that's a H, like this H here. That's a C, like the speed of light, like is up here. This is K, the Boltzmann constant. And this is T, the temperature in Kelvin, and then -1. And he took this equation and he basically did a curve fit to find out what this value H was. And he found out that this value H was 6.626 times 10 to the negative 34th. And the units turn out to be joule seconds. Remember, a joule is a Newton meter per second squared. A Newton is a kilogram meter per second squared, and then a joule would be a Newton meter, so that's a kilogram meter squared per second squared. So this is a kilogram meter per second, meter squared per second. So that's really what H was. It's called Planck's constant for this reason. And with that curve fit, he basically got the equation was identical to the actual experimental result. Okay, so that was beautiful. But in order to make that conclusion, he said that energy given off by these individual molecules was only equal to N times H times F. And in that case, N had to be 1, 2, 3, ... discrete amounts, okay? And it's called Planck's quantum hypothesis. But it's weird because he really didn't make anything about it. It wasn't very grandiose, and he didn't make any real big connections saying that, oh, I found something new about physics or anything big like that. He just said, hey, this is an equation. I know it works. This is, how I derived it. And I had to use this idea, right? It's only 5 years later that people make sense of what this is. It completely nails it. I mean, he gets the function exactly right. He wins a Nobel Prize for it. But he is a classical physicist. He is not a quote unquote modern physicist. He's just a brilliant classical physicist that was able to get a really tough problem solved. And he went on to do some good things in quantum mechanics, by the way. But like I said, he didn't realize the import of this. And really probably nobody did except for Einstein. So this was in 1900. Like literally the year 1900. Okay. So Planck did this in 1900. As I said, he won the Nobel Prize for it. And it did explain and get rid of the ultraviolet catastrophe. It gave us exactly that distribution. And it gave Einstein this idea of basically photons. Einstein pictured this and said that these quantum, which these quantum just means sort of discrete amounts. These quanta of energy are basically the molecules giving off a certain amount of energy. And that energy Einstein pictured as little photons of light, not not waves. We're going back against the wave theory of light, which is, Maxwell's creation, which is really Einstein's baby. Einstein got the special theory of relativity from Maxwell's equation, because Maxwell's equations are relativistically correct already. So Maxwell produced the idea that, and definitively showed with Hertz, that the light was in fact waves. And now Einstein's saying, okay, well, this now shows light's particles too. So that's kind of a big deal. But Einstein does it in 1905. What he does is explain that photoelectric effect we talked about. So this one was called the Ultraviolet Catastrophe. Whoa, I spelled that with a Y. What's wrong with me? Ultraviolet Catastrophe. Luckily, I wrote bad enough where nobody could read it anyway. So, so the ultraviolet catastrophe. Next comes the photoelectric effect. Sometimes people will actually write this as hyphenated. That's why I put the gap in there. I usually write it as one word, with photoelectric being all one word. So anyways, I just did it like that. That's the photoelectric effect. So Einstein said there actually exist photons of light, and they have an energy HF, and only HF. Okay, so that means atoms and molecules can only give off energy in the electromagnetic radiation or the electromagnetic spectrum in values of H times F for a particular frequency, right? So it's going to give off 1 HF or 2 HF or 3 HF or 4 HF or 5 HF, but nothing ever in between. It's almost like your speedometer. Those of you who drive a car with a digital speedometer will see, if you, well, unless it's like a Prius or something, if you actually hit the accelerator hard, a bunch of numbers will be skipped on your speedometer. But that's just delays in electronics. But imagine that being reality, that there's certain unallowed speeds. That's what this E equals N times HF was saying. So Einstein imagined that what was going on with the photoelectric effect was that the incoming radiation was actually hitting the atoms or molecules, depending on what the material was, and that those atoms or molecules were ejecting electrons. And when they ejected the electrons, they could only do so once a certain amount of energy came in. And that minimum amount of energy was the energy required to extract the electron from the atom or molecule. Okay. And he called that sort of the work function. There's a minimum amount of work you must do to separate an electron from its atom or molecule. And he said, well, what if the energy was actually HF? And that energy went into, that's the incoming light energy, is the HF. So let me write it that way. Incoming light energy was H times F. And that energy went into the kinetic energy of the electron that was kicked out, basically, plus the work function. Okay, so this is the kinetic energy of the electron. And this is the energy required to pull it out of the atom. Energy required to remove electron. Okay, so that was his idea. And then he said, okay, well, if you do an experiment where you cause the photoelectric effect to occur, in other words, you shine light on it and create a current, and then you adjust the voltage so that only the fastest of the fastest electrons can make it through, then you should get a result that looks like this. He said the max kinetic energy, in other words, this is the kinetic energy that the fastest of electrons has, is going to be equal to H times F minus the minimum work function. So basically what you would say is it's equal to the minimum amount of energy required, because the ones that were easiest to eject from the atoms, those are ones likely to have the most kinetic energy, because the smallest part of HF went into the W. So his idea was, if you make a graph experimentally of the maximum kinetic energy versus the frequency, you should have basically an F0, a minimum, if you will, at which there's any kinetic energy whatsoever, and then that should go linearly upward. And this HF0 would be W0. Okay. So you can figure it out that way, or you can just think about, okay, well, this is what's really going to happen is experimentally we should get this result, and then lo and behold, R.A. Millikin, famous for the Millikin oil drop experiment, the person that discovered that the charge of an electron or the electron's charge is a quantized thing, meaning charge only comes in multiples of E. 1.602 times 10 to the negative 19th. That was Millikin that did that. And this is the same guy. He builds the experiment and then adjusts the voltage so that he can find K max. And in fact, K max has to be equal to the electron charge times the voltage that you use to stop it. So what you do is you amp this voltage up backwards, and you keep doing it until it disappears, and then the last EV you had where there was a current, that voltage would correspond to the energy that the electron would have by voltage times E, the charge of the electron. Does that make sense? So Einstein proposed this in 1905. And just like Planck, evidently there's an E inside that O, and it wasn't meant to be. Einstein also won a Nobel Prize for this specifically. Okay, and this is in fact the Nobel Prize that he gave to his wife to get out of his marriage. So remember, I told you he promised her that if she just let him go, and she said she was a physicist herself and really a good one. She knew that he was going to get a Nobel Prize, so she said, yeah, sure. And he, of course, was good to his word and kept it. And Einstein actually was kind of a neat character. I mean, he was, one of the few people in America. He had just recently become a citizen of the United States and was very proud of that. He was one of the few people in America willing to write in the New York Times the problems with the disparity in the races and how America was seeing the black race as inferior, and how that was such an insult to such a great nation. So it's kind of neat to find that Einstein wrote anything like that. So that's nice. But at the same time, he was the same guy that, was had 12 mistresses at one time, and, put a kid in that was mentally handicapped in an institution rather than raise him. But again, that's sort of anachronistic analysis. Well, the adultery thing isn't, obviously, but the other thing is that was very common. That's what people did with handicapped people. So this was that. We now have an idea from this new modern physics that light now has wave-like characteristics. Okay, and we now have, and this is the part I meant, not the wave. It also has particle-like characteristics, and those particles are called photons. So in this, Einstein introduces photons as a thing. Okay. Now, Einstein spent the rest of his life trying to disprove quantum mechanics because he said God does not play dice. And what he meant by that was ultimately we get the Copenhagen interpretation of quantum mechanics is that there's this equation that Schrodinger comes up with that later has been shown to be exactly equivalent to Heisenberg's creation. But that Schrodinger's equation is this neat thing, and everybody in some sense knows it's right, but they don't know what the heck it means. That sounds super weird, and it is, okay? But basically, Schrodinger's equation says the second derivative of psi with respect to x squared, and this is just for one dimension, plus the potential energy multiplied by psi is equal to I h bar partial with respect to t of psi. Okay, that's Schrodinger's equation. We're not there yet. We haven't come even close to getting there. This doesn't come around until the 1920s. Okay, but this is Schrodinger's equation, and the problem is his reasoning for getting it seems perfectly correct, so everybody trusts it. But look, it's got an I in it. Does anybody recall what I is? Anyone? I give you a hint. It's equal to the square root of something. It's the imaginary number. And what we learned about imaginary numbers is they're freaking imaginary. They're not real. We should never have an equation about reality with an imaginary number in it, right? So that's jacked up. It turns out that's the only way you can make a quote-unquote wave equation. Believe it or not, this is a wave equation with a derivative in time, only a single derivative instead of a second derivative. Remember when we did the wave equation, ignoring this, you can sort of start to see that it's a wave equation. And in fact, what you have to have out here, I should have put this here anyways. I was using normalized units. Okay, you actually have to have that part too. Okay, h bar squared over 2 times the mass. This is Schrodinger's equation. If you get rid of this part, you can start to see it looking like a wave equation. But again, it has that single derivative in time. It turns out the only way you can have a wave equation that has a single derivative in time is if it's imaginary, because it has to have 2 components. But this is what his equation came up with. So they got this wonderful equation and everybody likes it, but what the crap is the psi? What is it? We don't know what it is. Well, it turns out that if you take psi and multiply it by the complex conjugate of psi, like this, then you get something called psi squared. And the nature of psi squared is that it's the probability, and this is the Copenhagen interpretation, probability of finding the object. This is the object that the equation is for, the object of mass m in a potential field V between x and x plus dx. So, for instance, the integral from a to b of psi squared dx is equal to the probability of finding the particle between a and b. So particle is at less than x equals b, but greater than x equals a. So that's what this is, and that's the Copenhagen interpretation. And you see, by multiplying it by its complex conjugate, you make it a real function. So it really is ultimately turning out to be something real. That's the Copenhagen interpretation, and that's where we're going with all of this. So that little sidebar is just giving you an idea of what's to come, right? We don't know that yet. We're doing early quantum theory where they're trying to reach this point, and even I'm trying to point out to you that even when they reach this point, they're like, well, what the crap is that? So this being a probability is exactly why Einstein was fighting quantum mechanics, because he says God does not play dice. He believed in a deterministic universe, which is the universe that Newton gave us, which said if you know at any point in time the mass and velocity that an object has, and you know all the forces acting on it, then you can predict where it will be at any point t in time later. Just by using the laws of physics. Now, it might be really hard to solve it, but he's saying in principle it should be deterministic. which is a really big thing. I mean, it literally would suggest that, for instance, our brains are all obeying the laws of physics and chemistry and biology. Therefore, our whole lives are sort of planned out. We're not even able to have a free will or something like that. That's the most extreme version of determinism. I don't think Einstein went that far, but in some sense, that's what the extreme version of determinism is. So he was really fighting the idea that the universe is not deterministic. He was trying to say it is deterministic, whereas quantum mechanics was teaching us that it was probabilistic. So it was so bad that when they found Einstein in his deathbed, he had a tablet on his lap, and he was literally the last thing he did was still trying to write field equations that could get rid of quantum mechanics. So obviously it was so important. He had massive tumor in his stomach and was dying of some horrible stomach cancer. But he was lying in his bed his last days, still writing out field equations, trying to get rid of the idea of quantum mechanics. So it was a really big deal. So we're now up to 1905. We've solved two of the major problems. We solved the ultraviolet catastrophe. We solved the photoelectric effect. We have not yet solved the distribution of matter problem, though. And the distribution of matter problem comes along with the plum pudding model. So now we're up to distribution of matter. And the big name here is Rutherford. Rutherford had a lab at Cambridge, and he was a really great experimentalist. And he's the one that said, "Science is physics, the rest is stamp collecting." So I kind of like him, and I like to bring him up to my geology and chemistry and biology friends. But anyways, he was doing an experiment to try to work out the details of the plum pudding model. So you remember we're talking in Great Britain here, so words don't necessarily mean what you think they mean. Plum pudding model. Any of you folks from Great Britain? I thought I heard an accent on one of my students, but I might not have. So in Great Britain, a pudding is not a pudding. Okay, it's not, and in fact, we wouldn't say a pudding here in America. We'd say pudding, right? But a plum pudding is sort of like raisin bread. In Great Britain, they would call it maybe a raisin pudding. Okay, so what they're imagining is basically matter is this big loaf of bread, like if you want. And the particles that had been discovered are like raisins in that raisin bread, or that plums in that plum pudding. Okay, that's the scenario. And in fact, we had discovered some particles. We had discovered the alpha particle, which we named alpha because that was the first thing we discovered. And it turns out the alpha particle is like a huge subatomic particle, which is an oxymoron, obviously, but it is it's a big thing. Okay. The second particle we found, we really got imaginative and named that the beta particle. That turned out to be an electron, or in fact, later we determined also that the beta particle acts just like another particle that we call a positron that we haven't offered yet, and we'll offer that in the next chapter. And then the third particle, again, they really got crazy, and they called it the gamma particle, and that one turned out to be the photon. Okay. So we had these particles. In fact, the lab that Rutherford's at is the same place where they discovered the electron. I mean, discovered the neutron. So these particles were coming into play and being discovered, and they were trying to make sense of where they were within all this junk. So what Rutherford did was the gold foil experiment. So imagine you could use aluminum foil, but why would you when you could waste the money on actual gold foil? No, there's actually a real good scientific reason for using gold foil. And basically what he did was he put a little sheet of gold foil, really, really thin, okay? And then he shot particles, alpha particles, at it, okay? Now, the idea being, if this gold foil is made of a plum pudding and these particles are so small, then you should get basically trajectories that look like this. They're going to go into, or into, or into, or maybe no deflection at all. But just little minor deflections is all you'd expect, because this thing is like 4,000 times as big as the beta particle. So the M of the alpha is on the order of 4,000 the M of the beta particle, right? So I really should not have used that color. M of the alpha particle is on the order of 4,000 times the M of the beta particle. So these are really big bombs, and they're being shot in this little collection of things that we think are comparable in size to the beta particle. And we're expecting small deviations. And from that, he's going to be able to map back from how these things are scattered, map back the positions of things that cause them to scatter. That was his plan. And the way he would catch them is he would put little detectors all along behind the gold foil. And by doing that, he'd know exactly where they ended up. He could pinpoint exactly where this beam would hit, and from that get nice little trajectories. Well, he said, because he's a braggadocious character, he said that he was being a very thorough experimentalist and made sure he checked, that nothing was coming back. So there was a detector back here, and lo and behold, one of the actual, or ultimately several, but initially it was one of the particles came back this way. Now, again, his story was that he was being a thorough experimentalist, but his lab assistant said, no, we just left one of those back there by mistake, and it went off, and we're like, what the hell's that? So he might not have been completely honest about the origins of this, but the big thing is he got Rutherford Backscattering. That's what this was called, Rutherford which is also Compton later talks about some scattering as well. But anyways, this backscattering was a really big deal. He said it was as if he fired a 16-inch cannon at a bowling ball and the 16-inch shell bounced back at it. Okay. Now we're talking around the era of World War I here. So the 16-inch shell literally means stuff that they use for war that are shot out of a barrel of a gun on a ship that's 16 inches in diameter. So you can imagine a bowling ball is pretty big, but compared to a shell that's 16 inches in diameter, it's pretty small. And that was how big of a surprise this was. We didn't expect it. And that's why we would not expect him to have actually put the detector back there at all. And it seems a lot more consistent with the idea that the detector was left by mistake and it made a noise or something. So because of this, we had to come up with the planetary model of the atom. So this all calls the planetary model. And this is the atom that all of you guys have probably seen before in cartoons and old literature and stuff like that, where basically you have a really small nucleus, say, and you have orbitals that look like this. Okay. In other words, the electrons, we ultimately figure out the electrons are orbiting around a central dense nucleus that in fact is very small, and 99.9% of the mass is in the nucleus, but the electrons are orbiting, and not all in one plane like we have with our planets, but in all planes are possible. And that's the planetary model of the atom, because the only way he could explain this was saying there must be something even more massive than the alpha particle inside of the matter. And they postulated the nucleus of the atom. Okay. It turns out they're right. That, just like the sun is well over 99.9% of the mass in our solar system. And it's well under 1/10,000th the size of the orbits. So its diameter is really small compared to the orbit's diameters. And because of that, it's really fitting mathematically, because it turns out if you were to expand the nucleus, scale it up, in other words, till it's the size of a grapeseed, the nucleus could be laid as the size of a grapeseed, could be laid at the center of the 50-yard line at my Washington football team's football field, and the orbits of the electrons would be out past the parking lot. So the scale is really right. That is actually turns out to be the scale is 1/10,000th of the size from the nucleus to the orbit is the size of the nucleus, and all the mass is in there. So that's the atomic model that we had to come up with. It's called the planetary model, and that led to another problem. That problem was that Maxwell's equations clearly state that when a charged particle, which in this case would be an electron orbiting something, when a charged particle accelerates, it produces electromagnetic radiation. It creates those electric fields oscillating and magnetic fields oscillating, going out at a velocity, and they carry energy. Therefore, these electrons would be constantly losing energy, and that energy would be lost basically to the kinetic energy of the electrons. So the electrons would slow down, slow down, slow down. And you know, for instance, if someone slowed down our planet all of a sudden, we would not be in a stable orbit where we are. In fact, the gravity of the sun pulling on our planet would force the planet to start to come in towards it. And in fact, it might get going so rapidly that it would run into the sun. Well, that's exactly what would happen with the electron. And they calculated that hydrogen, which is the most plentiful matter in nature, and in fact, we believe we have the hydrogen from the very creation of the universe. So that hydrogen would only last about 10 to the negative 9th seconds, if I remember the calculation correctly. So they calculated that according to Maxwell's equations, even hydrogen would be unstable, right? So that led to a problem. Bohr, who had recently finished his PhD, had studied the nucleus, in fact, and made models of the nucleus based on a liquid drop model and stuff like this, was a very brilliant man. Bohr, in fact, was not only brilliant, he was like, you know, I don't know, he's sort of like the stud that played on the Big Bang Theory. It was actually the same actor that played the dumb guy that said he made up the term hypotheses, but it was a different character that he played in this case, where he won the MacArthur Genius Award, and he was like the super handsome guy. He rode a motorcycle. He had a perfect head of hair. He was a super athlete. Well, that was Bohr. Bohr was like 6'9", 6'5", something like that. He was a professional soccer player. Like literally, he was good enough to play professionally. He was royalty. He made his own beer. He was the life of the party. He was a brilliant conversationalist. You could, you know, talk to him about anything, and everybody felt like, you know, they were the most important person in the room whenever you talked to him. So Bohr was just this perfect guy in like every way, and he turned out to be freaking so brilliant that he won a Nobel Prize, and even his son won a Nobel Prize. So Bohr comes along, and he wants to solve this problem, and he can't figure out any way to really solve the problem, but he knows the Balmer series. He knows that mathematical formula that comes up, and because of that, he's able to apply it in 2012. Yeah, he's able to apply it in the year 1912 and 1913. He goes to Rutherford's lab and sees these experiments, and he wants to explain it. And he knows basically that there's a difference in energy accounting for the actual colors that we see from hydrogen. So we're back talking about that spectra. So this is about the spectra. Now that we've gotten into the distribution of matter, we're now into the spectra thing. The little glass tubes, remember that when you put electricity across, light shines, and you get different colors for different elements and compounds and stuff like that. So what he does is he says, okay, well, I know this Balmer formula, and I know the Balmer formula says basically that there's an energy or there's some subtraction going on between wavelengths, and that subtraction gives me the wavelengths of the light that's emitted. And in fact, the Balmer series is given by 1 over lambda. This is the wavelength of the light emitted. 1 over lambda is equal to R, which we now call the Rydberg constant, and it's actually equal to R times 1 over 2 squared minus 1 over n squared, where n is equal to 3, 4, on up. Okay, so this is the Balmer formula. And really, we can now realize what it is basically all the things that are happening when light falls from, or excuse me, when the electron falls from the n equal 3 orbit to the n equal 2 orbit, or the n equal 4 orbit to the n equal 2 orbit, or the n equal 5 to the n equal 2. Those are all the very wavelengths that are predicted. This is the equation the mathematician had come up with. There was also a Paschkin series and a Lyman series. The Lyman series said that 1 over lambda, because they got the idea from Balmer, was in fact 1 over 1 squared minus 1 over n squared, where in this case, n was equal to 2, 3, so on and so forth. And then there was the Paschkin series, which is Paschen, and I'm really worldly ignorant, so this might be one of those things like salmon where I still tend to pronounce the L that you're not supposed to pronounce. So the Paschkin might not be supposed to be pronounced with the ch in it, but I am. So Paschkin was 1 over lambda is equal to r times, in this case it was really weird, it went the other way, it was r times 1 over 3 squared minus 1 over n squared. And of course, that meant that n had to be equal to 4, 5, ... So we had these 3 series, the Balmer series, the Lyman series, and the Paschen series. And those 3 series had equations, but like I said, I think Balmer was the one that started it all. And Bohr knew this. Bohr knew this, explained it. So he was trying to figure out some way he could get this result. And he knew he had to use the constant H. So Bohr knew this and suspected he had to use H. And remember, H is 6.626 times 10 to the negative 34th. And I made a big deal about this being a joule second. The reason why is a joule second. Remember, a joule is 1 Newton meter, which is 1 kilogram meter per second squared times a meter, which is a kilogram meter squared per second squared. And then therefore the joule second would equal 1 kilogram times meters per second. Okay. So this, for instance, is a unit of mass. This is a unit of distance. And this is a unit of velocity. So when you think about it that way, then you say, oh, well, that looks like angular momentum. So L, which equals angular momentum, also has units of kilograms meters squared per second. Okay. So Bohr comes up with the idea, maybe, just maybe, L, which equals mass times radius times velocity, is equal to n times h over 2 pi. Okay. And this quantity h over 2 pi had already been discovered. It's called h bar, and it's just h over 2 pi. Okay, so it's the same constant we used up here, only you divide that by 2 pi. So this turned out to be what he chose, and all he had to do to think about it was he needed to subscript the r. So he put a little sub n down there, because if you got an n on this side, something has to be discrete. And what he imagined was that there were allowed stationary states. So certain orbits which he called stationary states. Were allowed such that radiation did not occur. So he just imagined that. He said, well, maybe there's certain allowed orbits where Maxwell's equations don't apply. And if that's the case, then we'd have these stationary states, and these stationary states would not cause the electron to give off radiation, so the electron could stay there with no problems. He had no idea why that would be, but that was his hypothesis. And then all you have to do to get from there is you use Coulomb's law, which says, notice if you take the hydrogen atom, you got one proton and one electron. Both of those have the charge of E. So you'd have E squared over 4 pi epsilon naught R sub n squared. That's the strength of the force of attraction between the electron and the proton, right? Because they're oppositely charged. And that has to, of course, equal to the mass of the electron times the velocity of the electron squared over Rn. Anybody recognize V squared over R? Where would that come from? Anyone?
Centripetal, like, accelerate,
Exactly.
or like, yeah, uniform circular motion, whatever.
Exactly. So yeah, centripetal acceleration was the answer. Okay. And because of that, you can now say, well, wait a second. V is equal to angular momentum over mr, right? V is equal to angular momentum over m times Rn. So you could say V is equal to N times H bar, or H over 2 pi, over M times Rn. You now have E squared over 4 pi epsilon naught R N is equal to the mass of the electron times, now I'm going to square all this, I'm going to say N squared H squared over 4 pi squared, because the 2 pi's in the bottom here. And this is also going to be M squared. And this is also going to be Rn squared. It's Rn squared. Okay, now you can see this Rn squared is going to cancel out with that Rn. This 4 is going to cancel out with that 4. This pi is going to cancel out this pi. And we can get something to solve for R. So for instance, we can say, pull this Rn up top, and that Rn comes up top. Then I have also notice this mass right here will cancel out with this mass right here. So I'm going to say Rn is equal to N squared E squared epsilon 0. That's going to come up there. Ooh, not E squared. E is going to be on the bottom. Sorry about that. N squared epsilon 0 H squared. And then on the bottom, I will have pi times M sub E times E squared. Okay. So now he's got a orbit that would quote unquote be allowed, and you'd assume R would equal 1, 2, 3, 4, or N would be equal to 1, 2, 3, 4 on up for infinity. Okay. Well, if you combine that with the energy, you can ultimately find out exactly what Bohr did, and you actually get the very Balmer equation that was used. In fact, what Bohr ultimately got when you substitute wavelength and stuff like that in there, you can actually say that 1 over lambda. And by the way, I do this derivation on my YouTube channel if you want to check it out. But your book covers it as well. you get 1 over lambda is equal to, I will leave the Z off right now, but generally what he tried to do for any number of electrons that you might have around the nucleus of the hydrogen, well, I'll go ahead and put it down, would be Z, okay? So, or excuse me, for any number of particles in the nucleus. So Z would be Z squared times e to the 4th power times the mass of the electron, all that divided by 8 epsilon 0 squared h cubed. And then C times 1 over n prime squared minus 1 over n squared, where n prime would be the final n value. This gave R equal to the Rydberg constant, which is 1.0974. Excuse me, 974 times 10 to the negative, or 10 to the 7th meters to the -1 power. So we got you sort of there. You can see where stuff is coming from. I should have some E's in there. I should have some epsilon zeros, mass of the electron, some H's. You can see all that coming into play. Then it's just a matter of finding the energy of the orbital. And when you find the energy of the orbital, substituting that radius in, and all that works really well, and gave him exactly the Balmer formula. This is the Balmer formula, but it's also the Lyman formula. It's also the Paschkin formula, because this allows for any n prime, which in the Balmer case was n equal 2, in the Lyman case was n equal 1, and the Paschkin case it was n equal 3. And it explained what was going on. What it explained was that there would be a nucleus, say right here, and this would be n, and this would be n prime. There could be any number below this, by the way. And what happened was an electron happened to be here and fell down to here. And in doing so, it emitted a photon of energy E equals hc over lambda, which is actually the same thing as hf. I'm just using the fact that V equals C equals lambda times F. You can see that if I wanted to take the frequency and solve it for that, I get C over lambda. So I can take the C over lambda, put it here, and I get that expression. So what he's telling you is, oh, these lines that we see for, in those tubes with the gases in them are literally a signature of the atom or the molecule that created it, because it tells you the energy differences between two orbitals. And it says those energy differences, when you set them equal to HF, you get the frequency of those lines, or when you set it equal to HC over lambda, you get the wavelength of those lines. That's why they're a different color. Now, this worked perfectly, and this created the Bohr model of the atom. And that's something you learn about in your biology class. That's something you learn about in your chemistry class. But at the end of the day, it basically only worked for hydrogen. When he tried to do the exact same thing for the next most complicated, and by the way, this R does not include the Z. When he tried to do this for the next least complicated atom, the helium, it failed miserably. But you get the idea that Bohr is this one-hit wonder. No, Bohr continued to shepherd quantum mechanics through its discovery. Almost everybody that did anything in quantum mechanics worked with Bohr at some point. And Bohr was sort of the big brain overseeing all of it, even though it wasn't an organized system, because this was, multinational. We have de Broglie, who's I think in France. We've got Einstein, who's in America. We've got Heisenberg, who's in Germany. We've got Schrodinger, who I think is a Belgian. Is from Belgium or something like that. So you've got these people all over the place. And of course, Bohr is a Dane. He's from Denmark. And all these people are contributing to this. So there's no quote unquote manager, but if anybody was the manager, it would be Bohr. He's the guy that's putting this all together. And then just like later when we do the Manhattan Project, and Robert Oppenheimer, who also had worked under Bohr, by the way, became the next person to shepherd people along. Even though he wasn't nearly the caliber of Bohr, he was really still very brilliant. So this is the Bohr model of the atom. And the main thing you're supposed to get from that, and this is why they teach you in chemistry and in biology, is that every atom has a distinct set of energy levels that is a characteristic of that particular atom. And the idea of an electron transitioning from one orbit to the next is where we get these energy being put off, and we see it as certain allowed orbits. Now, ultimately, our idea in quantum mechanics is not these rigid orbits, these stationary states that Bohr hypothesized. And Bohr had no reason to understand why it was so. It was almost like God left us a little step ladder in front of the sink, so we could step up on the step ladder as a small child and see into the sink to see what was going on, just enough, not to see the whole picture, but just enough to make a next leap. So this particular happenstance that made nature match this particular dumb idea of the hydrogen atom was enough for us to start thinking about waves. We were thinking about HC over lambda and HF and waves and wave mechanics and stuff like this, all because of this little scene. It turned out to be completely wrong-headed, but it got us thinking about waves, which brings us into the next part of quantum mechanics, where we start to make an equation, which is Schrodinger's wave equation, and then Heisenberg does an entirely different, monumentally more complex, but also monumentally more simple way of attacking it, and gets a system that's so god awful that no one in the world uses it, and probably only him and Wolfgang Pauli, the only people that could possibly do it well. Also, Eugene Wigner could do it as well, but those are probably the only people. So anyways, the Bohr model of the atom solves the Spectra problem, and of course Rutherford spawned that by Bohr by his discovery of the planetary model of the atom. So we've now solved all those problems, and then what comes of quantum mechanics is quite beautiful. So one of the next things that's going on, so that was in 1912, 1913. Of course, Bohr did win a Nobel Prize for that, as is the common trend amongst people doing these things. The next part of the story comes along with Compton, who around 1923, so this is sometime later, Compton noticed something called the Compton Shift or the Compton Wavelength, further giving strength to the idea of electrons or of photons being emitted. Okay, so what Compton did was Compton looked at photons that he sent into electrons. So he would send a photon. So we're talking about Arthur Compton. Oh, excuse me. I don't know how I was putting the two there, but anyways, he's sending photons to run into electrons. So here would be a little electron. And what would happen would be the electron would take off at some angle. Let's call that angle theta. And then the photon would actually do something quite miraculous. The photon would come off at an angle, let's say phi. Notice I changed colors there, and notice that my wiggles aren't the same distance apart. So what I'm saying here is, in this case, the wavelength is that, and in this case, the wavelength is this big thing, right? That's what Compton found. And in fact, Compton found that the final wavelength, which we call lambda prime, Compton found that lambda prime was equal to the initial lambda plus h over MEC. I derived this, by the way, on my YouTube channel as well, so you can check that out there, times 1 minus the cosine of the angle phi. So this is the Compton Shift. And I'm pretty confident he won a Nobel Prize too, but I don't recall reading about it. But I want to say he almost certainly did. Oh, by the way, your book does the derivation of the Compton Shift as well. So this is the next big thing. And in fact, we call something the Compton Wavelength. And that's actually equal to H over MEC. And you can see where that comes from. Obviously, this whole thing has to have units of wavelength since it's being added to a wavelength. This has no units, so that must have units of wavelength as well. It turns out the Compton wavelength is 2.43 times 10 to the negative third. Or excuse me, 2.43 times 10 to the negative third nanometers. And of course, a nanometer, or excuse me, a 10 to the negative third nanometers is a picometer. I'm going to write this again because it got ugly over there. Okay, so that was another result. And in fact, that showed us that these photons, energy is definitely related to their wavelength and inversely so. And that's completely consistent with the idea that E equals HF gives us E equals HC over lambda. You see that when lambda goes up, the energy goes down. And when lambda goes down, the energy goes up. So obviously, if the photon comes in and hits this electron, some of its energy is going to be stolen. And you might think, oh, well, that means the photon is going to slow down. No, this photon is a particle of light. It will always travel at the speed of light, right? So you can't do that. In fact, the way it loses energy is by increasing wavelength or decreasing frequency in either way. So the other relationship is frequency goes up implies energy goes up, and frequency goes down implies energy goes down. Those are thumbs up for energy and frequency, thumbs up, thumbs down for energy and wavelength. Okay, so that's another neat result, and it's something that we can make use of. You actually have to use relativity, though. The relativistic momentum has to be used to derive this. And like I said, you'll see it on my YouTube channel, or you can just look in your textbook for its version. They're probably almost identical, if not identical. The next thing that happened was we discovered pair production. It was discovered, for instance, this is pair production. And pair production was sort of discovered around the 1923 era, around Compton scattering, basically. So I'll just say circa 1920s. Okay. And with that, what we discovered was that you could have a photon actually, this might have been quite a bit later than 1920. So let me put a bar through that because something has to happen for this to actually occur. A photon will be moving along, and then spontaneously the photon will disappear, and out will pop a E positive and a E negative. This is a positron. This is the antiparticle of an electron, which we haven't even discussed yet, but that actually occurs. And all that has to happen is that the energy of the photon, which equals HF or equals HC over lambda, that has to be greater than or equal to 2 times the mass of the electron times c squared, because electron and positron have the same mass. So it turns out when you have an electron or photon with that much energy or more, okay, then spontaneously a photon can disappear and become a pair of protons, or excuse me, a pair of electrons and anti-electrons. One electron, one anti-electron. So now we've seen sort of different ways photons can behave. They can lose energy by gaining wavelength, increasing their wavelength. They can gain energy, of course, by shrinking their wavelength in theory. or they can just spontaneously disappear and create a proton, I mean, an antiproton. Dang it, why do I keep saying that? An electron positron. I keep wanting to use the word positron, and I say proton instead, and I just don't know. So that's a whole neat thing, and that's really part of the discovery that Bohr made, is when the electron falls down from the n prime orbital down to the n orbital, like I had drawn previously. It's not that the atom or the electron was holding on to a proton, to a photon, because photons don't stop. They have to move at a speed of light, period. But what happened was an electron was up here, comfortable at this level. Spontaneously, the electron disappeared, a photon was created, and an electron reappeared, identical to the last one, right in this spot. Okay, so this is making sense of what photons do. I will leave it up to you to figure out the time period, because I think it's got to be much later, because I know Dirac is the one that hypothesizes the existence of antiparticles, and he does so for a crazy reason that I think you guys will get tickled to hear. So I'll leave it at that. The next thing is the wave nature of matter. Now, this one has a story along with it that may or may not be true, but I like it so much I continue to tell it. And the history that I've read of it, I don't think it's actually true, but it's kind of cool to hear about. So there's a guy by the name of Louis de Broglie. So this is 1923. Exactly. I know that one for sure. Okay. A guy by the name of Louis, L-O-U-I-S, de Broglie. And I have no idea if I'm pronouncing his name correctly. He's noble from two lines. This I know. This part I know. He's nobility from two different lines, two different countries. One's France, and I think the other one's Germany or something. But he's definitely nobility, and he's sort of dipping, if you will. The wealthy people, the nobility, are supposed to leave certain realms for the non-nobles, the plebes like us, and they're supposed to leave that by like not pursuing college degrees and stuff like that. Of course, Galileo was one of those people that was using degrees and things like that to move ahead, and that was fine because he was born in sort of a poor guy, but he got wealthy, and then that sort of changed, you shouldn't be doing this anymore. Well, this is one of those scenarios where he's going to get his PhD. And people are really impressed with him at his university or college or whatever. And they're like, he's really a smart guy. But purely based on beauty and symmetry, which I've talked to you about how physics is dictated by that, he basically says there's no way in heck God is going to create a universe. And I'm not saying he made the God argument. That's just a phrase that we use like Einstein does. God would not play dice. But I'm going to say that there's no way the universe should exist where radiation / light has wave and particle characteristics. Okay, we know that. We've now established that through the photoelectric effect and all this stuff, that light, which we think of as waves, has this duality of being like particles, namely photons. De Broglie's argument is there's no way nature would allow this to be unless you say that matter has both wave and particle characteristics. Okay, no way, right? So based on that, he then basically does unit analysis to find out some way he could relate lambda to h. Okay. His idea is that lambda is equal to h over p. That's his big equation. That's his thesis. And the story I was told, again, this is the story that may be apocryphal historically, but I love it. The story that's told is people are kind of upset about this because this guy's brilliant, but they think he's a nutball for offering this suggestion. So not only that, they've got the problem of him being double nobility, which that is a fact I do know. And being a double noble, you probably would be well advised not to tick him off, or not to tick off his family by saying that he's a crazy person, or by not giving him his PhD because he's clearly a crazy person, right? So what they try to do is skirt the lines, if you will, by repeatedly assigning him a date, time, and location for him to defend his thesis, to do his dissertation, basically, and then changing it and not telling him. So the story goes that he repeatedly shows up for his dissertation and there's nobody there. And then he'll like go to the office and they say, oh, I'm sorry. I thought you knew we had moved it to such and such. And evidently this happened a couple of times. There is some evidence that it was moved a couple of times. So I suspect there might be some truth to it. It might be one of those things that you're never going to find written because it was never written down. They would never write such stuff down. But that, you know, people that maybe worked at the university, some of the other, you know, faculty members might have told other faculty members that they were doing that. So there might be some truth to it, but it'd be really hard to confirm. But eventually what ultimately happens, and this part I know is true as well, Einstein becomes famous. Notice this is 1923. Einstein writes his special theory of relativity in 1905. And then in 1921, we finally get confirmation that light is in fact curved by gravity, and Einstein becomes a superhero overnight. I mean, he already was within the scientific community, but now he's like famous, where he was on the cover of the New York Times and they said, God said, let there be light, and Einstein told it how to move. That's the kind of headlines he got. And like I said, despite his beauty, which I don't think is all that impressive, he did have, quote unquote, 12 mistresses shortly after this time period. And Jay Leno funny said, wow, to have 12 mistresses, you'd have to be oh, yeah, that's right. So again, I'm not trying to glamorize adultery or anything like that, but just know from the time period, for someone to have 12 women, that would probably suggest that he was impressive in some way. And it's not often that scientists are rock stars, and that's sort of what he became. So he comes along traveling the world after, you know, this discovery of the bending of light was actually true, that he had, you know, predicted. And he stops at this university and says, oh, this is really great. We've got a really a big issue here. We're not so sure about this person's thesis, and we'd like you to take a look at it. And Einstein says, okay. So Einstein reads de Broglie's thesis and says something along the lines of, it's the most beautiful insight that I've seen in decades. So immediately they give de Broglie his PhD. And in fact, he wins a Nobel Prize. And then later, they're actually able to take electrons and fire it at those arrays of atoms. Remember how I told you in a solid, the atoms make little matrices, or make little, just basically little patterns of matter. Those are sort of like little thin slits, if you will. The distance between an atom and another atom is a very small distance. So if you fire electrons through that, that distance is comparable to what this wavelength you'd expect to be. So you should get the idea that an electron would behave like a wave, if it's going to be a wave at all, only when the wavelength is comparable in size to the hole that it goes through. That's the nature of diffraction and wave nature, is they only bend and interact with things when they're comparable in size. So by using the lattice of atoms in a solid, you could fire electrons at the lattice of the atoms, and the atoms would actually, the separation between the atoms would act like slits, and then you could basically calculate the wavelength of the electrons. And it turned out that de Broglie was not only right about electrons having a wave-like characteristic, he was also right about the equation, which, as I told you, was purely a matter of doing unit analysis. Remember, chapter 1, I told you it's important to figure out, you know, relationships between units or dimensions. That's all he did to get this. And doing that, he was able to show that matter actually had a wavelength and got the right formula. And when we did it using, I was trying to remember the name of it. It's Bragg. I want to say it was Bragg, but I don't think it is Bragg. Anyways, there was some electron scattering off of atoms, and that diffraction was calculated and determined the wavelength to be exactly on par with this. So we had another neat discovery. This was all early quantum theory, and they were trying to put all this together. Again, you don't see anything like a Schrodinger's equation coming out of this. All you see is this hodgepodge of crap where evidently now photons exist. Evidently now particles of light exist. Evidently now those photons can only gain or lose energy by changing wavelength or completely disappearing, right? And lo and behold, matter, which we've known for years, since 1905 at least, known definitively that atoms were made of matter and therefore particles, but now all of a sudden it's also made of waves. So that's some crazy crap that they're dealing with, and that's what they were facing. But the neat thing is, in 1923, Bohr now has a really good explanation for his stationary states. It turns out that if you look at the Bohr model of the atom with a nucleus, okay, and then you take the first orbital, n equal 1, remember we said that L would equal m times Rn times V, and we said that m times Rn times V was equal to n h over 2 pi. That was Bohr's quantum-like hypothesis, okay? Well, you can see from this that 2 pi times r, if I pull this 2 pi over here with that Rn over there, is equal to n h over m v, okay? That doesn't look that bad, but what it tells you is that the distance around the nucleus on an orbit has to be either one wavelength or it could be two wavelengths, or it could be three wavelengths. In fact, we find that R sub n is just equal to n times 2 pi lambda, where lambda is the wavelength of the electron. Okay, which you can see there, that is n times h over p, which is exactly de Broglie's relationship. So now in 1923, de Broglie offers this. Einstein loves it. He gets his PhD. You can look back at Bohr and say, oh, well, here's the reason for your stationary states. It turns out the electron is an actual wave, and the stationary states are actually the wavelength of the electron oscillating in the only way it could, because if it's not a standing wave, then the wave's not going to be stable. So now you've got a reason for stationary states. They're just standing waves. And what I was telling you earlier about, you know, getting that little ladder to let us look over the edge as a small child into the sink, that ladder that allowed us to see waves as an important part was this very fact. De Broglie discovering that matter is made up of waves makes us think in terms of waves. We know from what you learned in simple harmonic motion and the wave chapters, we know that the solution to a simple harmonic motion problem and also the solution to a wave equation is something like e to the I kx minus omega t, right?
we also know that omega is equal to 2 pi times f, and we know that k is 2 pi over lambda. All these things we learned from, well, except for this, we learned this in the rotational motion part, but we also learned this again when we did simple harmonic motion and wave motion. And we found out that the wave number k was 2 pi over lambda. This isn't the Boltzmann constant, in other words, right? So if you try to take energy and say energy is equal to kinetic energy plus potential energy, okay, then you might want to say, okay, well, I know the energy E should be H times F, which is also H bar, H over 2 pi times 2 pi F, which equals H bar omega. See that? By changing H to H over 2 pi and F to 2 pi F, those two pi's cancel out and I get H omega. So Schrodinger is able to look at this and say, this is a solution of a wave equation. Let's call it the wave equation psi. Maybe there's going to be a constant out in front. And he says, wait a second, if I take the derivative of psi with respect, and I actually should be using a partial derivative here, partial of psi with respect to x, then I would just get derivative with respect to x would be I k a e I to the kx minus omega t. Okay, and then the second partial of psi with respect to x squared would be I k squared times a e to the I kx minus omega t. And he says this partial of psi with respect to t would be equal to negative I omega a e to the I kx minus omega t. Okay. So the second partial of psi with respect to x squared is actually equal to negative k squared times psi. Because I squared, of course, is negative k squared times psi. And of course, k is 2 pi over lambda. Okay. And partial of psi with respect to time, we found was negative I omega times psi. Well, if I multiply this by h, then I could actually get an energy. So let's say I times h bar times the partial of psi with respect to t. Notice what happens. So I'm going to multiply I and h bar times partial of psi with respect to t. The I times the I is going to give me -1. And then the negative is already there. It's going to make it +1. So I get h bar omega, which is just E. That's the energy, right? Now check this out. What if I multiply h bar squared over 2m times the second partial of psi with respect to x squared? Well, if I do that, I'm going to get h bar, so it'd be h squared over 2 pi squared times m times the second partial of psi, which is 2 pi squared over lambda squared, right? Because that's what k was, times psi. This was E times psi, by the way. So I now see this 2 pi squared, this 2 pi squared cancels out, and I get h over lambda squared times 1 over m times psi. Does anybody recognize what h over lambda would be according to, I don't know, something that you might see here? What's h over lambda? Oh, and I left off a 2, by the way.
The momentum?
It's the momentum. So in fact, h bar squared over 2m d2 psi over dx squared is in fact equal to p squared over 2m psi, right? And does anybody recall what p squared over 2m is? Work it out. You know, p equals mv, and do p squared over 2m. What do you get?
One half mv squared.
Yeah, 1/2 mv squared. Very good. And that's in fact kinetic energy, isn't it?
Yep.
So if you take E and set it equal to just potential energy, or excuse me, just kinetic energy, let's ignore the potential right now, then the way to do that in terms of a wave equation would be saying h bar squared over 2m second partial psi with respect to x squared is equal to IH bar partial with respect to t of psi. That's Schrodinger's equation. And I suspect this is what Schrodinger did. I don't know that it is, but it seems like a fairly reasonable thing. And then if you want to add the potential, well, it looks like, multiplying this thing times sine is the deal. I mean, obviously this is E times psi. So multiplying by psi seems like a perfectly reasonable thing to do. So it ultimately becomes negative h bar squared over 2m. And actually in 3 dimensions, it becomes del squared psi plus v psi is equal to I h bar partial of psi with respect to t. And that is the actual total Schrodinger's equation. So that's what I mean by we were able to look over the edge of the sink with a little step stool that God or the universe left us and made us think about waves. That makes Schrodinger think about a wave solution. And then he just used something we always know, E equals, in one case for a free particle, it's just equal to its kinetic energy. And he starts taking derivatives and can come up with a wave equation. And this is called Schrodinger's, Schrodingers equation. And it turns out that equation is right, by the way. It's 100% correct. Well, 100%, except it's not relativistically correct because we used p squared over 2m equal to the kinetic energy. Dirac comes along and uses the proper version of kinetic energy and comes up with a much more nasty, it looks prettier and it looks easier, but it's not easier, and it is prettier, but it's not easier, okay? And the problem with that is he publishes it and says, this is the relativistically correct quantum mechanical equation. And everybody says, well, that can't be right. It's got negative energies. He said, my equation is right. In fact, what must be the case is there must exist particles of antimatter. And when you see a negative energy, that's the energy an antiparticle would have, only it's positive. So basically, Dirac was so cocky that his equation was correct, that he predicted the existence of matter that had never been seen before. He predicted the existence of the anti-electron, the positron we call it, the antiproton, the anti-neutron, quarks, anti-quarks, all those things are all antiparticles and all antimatter. And he predicted it purely from his Schrodinger equation having negative solutions. And guess what? He was right. So it's really cool. But in the meantime, while this is being done, Heisenberg goes off on a tangent. It's the craziest thing. He basically says, hey, what can we actually study, or what can we actually measure in our lab? I can only measure transition probabilities, of, say, an electron going from N1 to N2. And what he discovered was that there was a way mathematically for you to calculate that out that was basically just matrices multiplication. So the multiplication of matrices. And in fact, he knows Jordan and works with Jordan, of the Gauss-Jordan method. He knows and works with him and comes up with these matrices that he's able to explain. And because of these matrices, he comes up with an entirely different Schrodinger equation, or excuse me, an entirely different version of Schrodinger's equation that's called the Heisenberg's equation. And he completely creates something that just no one could possibly understand. And in fact, he gives it to his PhD advisor, whose name escapes me right now. And that guy's like, okay, well, I'll just put this off. And then Heisenberg goes on vacation. He just goes on a hiking trip, leaves it to him, and asks him to publish it. And he says, okay. So he's reading over it and he's like, oh my God, this is brilliant. And he publishes it, of course. And it actually produces the famous Heisenberg uncertainty principle. And it has to, because with that mathematics, there's no way you can't, because it's just a Fourier transform from one variable to another. And he finds that delta P sub x times delta x, which are two measurement uncertainties, the uncertainty in the momentum in the x direction times the uncertainty in the measurement of the x position, is got to be greater than or equal to h bar, which is h over 2 pi. That's a fundamental result coming out of Heisenberg's version of this. And it looks horrible. I mean, what Heisenberg does, but it's exactly right. And later it takes a guy by the name of Eugene Wigner to actually show it. And Eugene Wigner is another one of these brilliant guys from Budapest, Hungarians. There's all these brilliant Hungarians working on this stuff. Enrico Fermi marries Eugene Wigner's sister, for instance, and Fermi goes on to create the first nuclear reaction. And in fact, is sort of the brains behind Oppenheimer's Manhattan Project. And that's why we have Fermi Lab up in Chicago. Meanwhile, Eugene Wigner wins the Nobel Prize, not only for showing that these two, Heisenberg and Schrodinger equation, are equivalent. He doesn't win a Nobel Prize for that. He wins a Nobel Prize for basically discovering the electromagnetic quantum mechanics. In other words, Maxwell's equations have to be fixed for quantum mechanics. And that's called QED, quantum electrodynamics. And him and Toshiko Manga, I can't remember his name. It's a person from, I want to say, Japan. Him and that guy and Richard Feynman, all share the Nobel Prize that year for independently, three of them discovering the quantum electrodynamics. So that's Wigner, the Hungarian. Hans Bethe, B-E-T-H-E, is another Hungarian. He's the guy that discovers the mechanism by which the sun works, basically the proton-proton chain, and later the CNO cycle by which the sun works. He's another Hungarian, and he also happens to be one that works on the Manhattan Project, and Feynman works quite a bit with him. And then there's another one whose name right now is escaping me, Szilard. That's it, Szilard, S-Z-I-L-A-R-D. He's one of the smartest idea men in physics, but he never does anything. In fact, people that you listen to interviewed from the Manhattan Project said they never saw him do a bit of work. He's just walking around all the time. Well, he's the one that got Einstein together and drove across the country to deliver a letter to the president about the urgentness of us building a nuclear weapon using E equals MC squared, specifically because the Germans, from which Einstein recently left, are the leaders in science on nuclear physics. So Szilard, yet another Hungarian, convinces Einstein to do that, and Einstein and Szilard and another person all drive across the country. Einstein at the time was, I think, in California. He might have been in Princeton, New Jersey by then, but I think he was in California. But anyway, he drove across the country and met with the president and told him the urgentness, and that's what started our Manhattan Project. Meanwhile, other Hungarians are solving differential equations, and so you'll run into their names in there with regards to electricity and magnetism and more advanced courses. So it's kind of crazy. I don't know what's going on in Hungary at that time, but they produce like 12 people that all come to America and win the Nobel Prize. So anyways, that's it. That's all of the early quantum theory. You can see the outlines of all the equations. You can see applications, which are really cool. So I definitely recommend you reading all the chapter and looking for the actual applications of this, because there's actually numerous ones. and you can see some simple physics problems to study. We are going to have a quantum mechanics related test, and you can see I've already posted a quantum mechanics practice exam, and that's sort of the keys of what you need to know about quantum mechanics. We've just covered the first chapter of it. Next time we'll cover the next chapter of it, which will be 38, and that's the actual quantum mechanics as opposed to the early quantum mechanics. And then in fact, you'll look at that picture and you'll see at the opening of chapter 38, which is page 1017, this is a Solvay conference where they basically were hammering out the interpretation of quantum mechanics. And it's probably the most valuable collection of human beings in the history of mankind. Meaning these people are the underpinnings of everything great that's happened to the world, but also some bad things that's happened to the world. I mean, we have, for instance, nuclear weapons now, but we also have nuclear energy, but we do have nuclear weapons. We have radiation treatments for cancers that are actually working really well. And all of these people are responsible for that in some way or other. They include Picard, Ehrenfest, Schrodinger, Wolfgang Pauli, Heisenberg, Debye, Bragg, Dirac, Compton, de Broglie, Max Born, who's the great-grandfather of Olivia Newton-John, by the way. That's kind of a cool tidbit of information. Niels Bohr, Max Planck, Madame Curie, H.A. Lorentz, Einstein. That's some of the people that are at this picture, so I definitely recommend you checking it out. Our time is almost up, but I'm going to go ahead and let you go anyways. And I will see you guys at 12:45 for lab, and I'll wait for the last person to leave in case anyone has any questions.
Didn't Einstein use particle physics to disprove gravity as a force, though? Like you're talking about
not really particle physics, but he did sort of get rid of the idea of action at a distance using general relativity. In other words, general relativity is ultimately a field theory. It postulates the existence of the universe being a four-dimensional field, x, y, or x is left, right, y is in, out, z is up, down, and time being the fourth dimension. And you don't have to think about a force at all. In fact, gravity is not a force, but gravity is also not a particle thing. You're sort of intertwining some stuff. Gravity is not a particle thing, not yet, anyways.
That's what I was getting at.
Yeah,
because it doesn't have a correlating exchange particle.
Exactly. If a graviton exists, then we could make a quantum gravity idea. So there's two candidates for that right now: quantum loop gravity and string theory. And neither one of those are doing well. Neither one of those are to the point where we can discern them from general relativity. Specifically, they get exactly the results that we already knew, but it sort of predicts them. Like if we had discovered this beforehand, we would have predicted those results. But the problem is we don't know how much of that was cooked into the way we made it. So we might just be, patting ourselves on the back. Oh, good job. You just made up the thing you made up, right? So that's the problem with it. And the experiments that need to be done that could actually separate it from general relativity are so far in the future technologically that they're not really in any sense a more than a hypothesis at this point. But both of them are good candidates. It's just a matter of we're not technologically ready to test either one of them. So we stick now with the four-dimensional continuum of space that general relativity gives us. But we know there's going to be some problems because space is not only that big thing that we use in relativity where it's a continuum. When we get down on the microscopic level, that pair production stuff that I just showed you happens all the time. Like matter, if you get down to space at the smallest level, say 10 to the negative 43rd meters across, you're going to see matter or space is sort of a frothy, bubbly, boiling surface where particles are being created and destroyed every instant. And there's no continuum of space possibly. So yeah, that's the problem of all that.
Yeah, wasn't some of Schrodinger stuff showing that like some stuff blinks in and out also? Like it'll be there and then it'll not be there like in a second. Was it like
Yeah, that's the Schrodinger's cat
photon
type
or
thing.
matter or something?
Yeah, so basically when they finally figured out what that psi was, the wave function, it's a probability distribution. It turned out one of the ways you can look at that is if you set up a Schrodinger equation for an electron that has, say, 40 different routes it can follow, then it'll have a little probability distribution for each of those routes. And the instant you actually measure it, all those other probabilities go to zero, and then that one mount is the only thing that's left. So a lot of different ideas can come from that. One of them is that a cat's neither dead nor alive until someone observes it, you know, ignoring the fact that the cat could be an observer of his own life. But in general, the idea still stands. You put a cat in a box that's sealed up. You can't make any noises or hear any noises out of it or anything like that. And you put inside of it a nuclear disintegration triggered cyanide capsule. And while he's in there, since nuclear disintegration is a random event, we never know when the actual nuclear disintegration occurs. So the cat is both dead and alive at all instances. In other words, it has a psi wave function that has a dead lobe and has a live lobe. And both of those lobes are the state of the cat. And until we open up and observe it, the cat is neither dead nor alive. That's the same thing with particles. The particle is actually at all places until you observe it, and then it's that one thing, and they call that the collapse of the wave function. Basically, all the probabilities collapse when you observe, and the only thing that's left is the 100% probability of the one thing that you did observe.
Yeah, it's weird.
Yeah, it is really weird.
Anyways, I'll see you in a bit.
All right, see you. Anybody else?
Well, today's lecture should be uploaded today.
Yes. In fact, the last one I couldn't because I lost everything but like the first 10 minutes when I did that break. Actually, I lost everything but the first hour. But yeah, I'll put it up immediately. I'll try to do it while you're in lab, in fact.
Okay.
Anybody else? How about you, Emily? Rosa, Jack, anybody? All right, I'm going to go ahead and call it out, and I will see you guys in about 30. Those of you who have me for lab anyways.